Good afternoon everyone. I am Chanda Devna, one of the PMRF fellows of ISA Badhampur. So I am the TA of this course Reagents in Organic Synthesis, instructed by Professor Subhash Chandra Pran from IIT Guwahati. So in this class I usually discuss about some important topic of based on this chapter, and also I am trying to solve some previous year NET and GATE questions which may help you to solve your upcoming assignments and also your examinations. So let's start. So sulfur in organic chemistry. So sulfur is one of the important element for our periodic tables and in our organic chemistries also, because you can use this as a reagent and also in different type of as a substrate also. So in the last class I had discussed about some questions based on this sulfur chemistry. So just continuation of that, let's solve some questions. So what will be the, we have in the last class I have discussed about this sulfur halide. So this is called sulfur halide. Whenever there is a adjacent positive negative charge, is called a halide. So if a positive charge is on sulfur and there is a negative charge just adjacent to that, that is called sulfur halide. So whenever the sulfur is oxidized in its oxidation state, then it is called sulfoxide halide. This is called sulfoxonium halide. This type of halides are called sulfoxonium, and this is called sulfonium. This is called sulfonium and this is sulfoxonium. So whenever you add this type of sulfonium halide in a ketone, what happens? So usually there is a formation of epoxide from this ketone. So what will be our A? So after the reaction of this sulfonium halide, this reaction goes something like this way. So this CH2 minus attack to this carbon center and this open up. After that, similar to the phosphonium halide, then this attacks to this place and it gets removed from the system. So as a we get a epoxide. Now if we add sodium amine into it, what will happen? This NH2 minus will attack to this epoxide and it will open up this 3-member ring. Now we know that amide usually prefers the site which is less sterically hindered. So now we'll get now in presence of HNO2, this amine will be transferred to a diazonium. It's a very old chemistry, I think everyone is aware of that. If we add HNO2 into NH2, it will transfer to a diazonium salt. Now in presence of this O minus will come here, and this bond will shift to this carbon. This is called semi-pinacol-pinacolon type of reaction. This is called semi-pinacol-pinacolon type of reaction. So there will be generation of 8-member ring because one carbon extension. So there will be a generation of 8-member ring. So from 7 we are getting a 8-member ring. 8-member. Okay. So this is called a semi-pinacol-pinacolon reaction. What it is called? Semi-pinacol-pinacolon reaction. now there's a question. In a same substrate, if you add sulfonilamide and if you add sulfoxonilamide, what will be the difference in that? So as I have discussed already, if you add sulfonilamide into alpha beta unsaturated double bond, this is called alpha beta unsaturated double bond. This specifically reacts with the ketone center. But whereas if you add a sulfoxonilamide into an alpha beta unsaturated ketone, this reacts specifically with the alpha beta unsaturated double bond center. This reacts with the alpha beta unsaturated double bond center. So in this case we get a cyclopropane type of product. In this case, we get a cyclopropane type of product, whereas in sulfonilamide, we get a epoxide as our product. Okay. So, understood everyone? So let's go to our next question. Sulfur in organic chemistry. Both the dimethyl sulfonium methylide as well as dimethyl sulfonium methylide react with the same way to give epoxide on reaction with non-conjugated aldehyde and ketone. So whatever I said, if you take a simple ketone or aldehyde, it will give both the ylide will give us the epoxide. But if it is a alpha beta unsaturated ketone or aldehyde, then sulfonilamide will give specifically epoxide, but the sulfoxonilamide will react with the alpha beta unsaturated double bond and will give a cyclopropane type of system. So with sulfonilamide, the epoxide has a formation of new carbon-carbon axial bond. So now if you add this type of ylide in a different type of substrate, like this type of cyclohexanone, what will happen in two different ylides? So if it is sulfonilamide, the epoxide has a new carbon-carbon bond. If it is a sulfonilamide, this prefers to attack from the axial side. Whereas if you take the sulfoxonium, because this is bulkier, than sulfonilamide, so this prefers to attack from a equatorial side. Okay, this prefers to attack from a equatorial because this is bulkier than that of the sulfonilamide. In this case, you will always get, in case of sulfonilamide, it will always get an axial epoxide, that is where the carbon-carbon form from the axial plane like this. And if you get this use this sulfoxonilamide, you will get formation of a equatorial epoxide, that is where the carbon-carbon bond form at the equatorial place. Okay, so it is suggested that this difference may also be due to the reversibility of the addition in case of sulfoxonilamide, and the product from the sulfoniamides is due to the kinetic presence of the axial addition by small nucleophile, and in the case of reversible addition of sulfoxoniamide, product stereochemistry is determined by the rate of the displacement, which may be faster for the more stable epoxide. Okay, because of that, as in case of sulfonilamide, the reaction process is irreversible, but in case of sulfoxonium, the reaction is reversible, so it takes time, and because of slower rate and bulkier, it always prefers the thermodynamic product, that is the equatorial carbon-carbon bond. Sulfur in organic chemistry, there is another example. If we add this type of anion to this ester, it can kick out the OAK and it will form this type of thioester. Now if we add Cl back to back this range, what will happen? Yes. Can anyone guess what will happen? If you add, so this hydrogen is acidic. If you add this base, what will happen? It will take up a proton from this place and generate a negative charge here. After that, if you add this negative charge to this bromo ester, it will kick out the bromine from the system and form this type of after that, so it will just after that if you add a zinc acetic acid, what will happen? It will just break the carbon sulfur bond. It will just break the carbon sulfur bond and we will get this type of 1,3-diketoester. Sorry, 1,4-diketoester. So like this way, just by using this reagent we can form a 1,4-diketoester. The next application of sulfur is 1,3-di, in Umpolang, that is called dipole inversion. Suppose a reactive center has a inherent polarity. Like suppose a reactive center is electrophilic in nature or nucleophilic in nature. Umpolang means you can just reverse the polarity of the reactive center. Suppose if it is inherently, if it is a electropositive, that is a electrophilic center, and you are turning it to a nucleophilic center, this is called the reversal of the polarity. That is Umpolang. Okay, so by using this type of 1,3-diol, we can 1,3-dithione, we can use this Umpolang, where it will react first. This 1,3-dithione will react with this ketone in presence of H plus, will form this dithioester. After that, if you add a base and take up a proton, now because of this minus I effect of this S groups, this hydrogen become highly acidic. Now in presence of base, you can take up proton from this place and generate a negative charge, and after, if you add a electrophilic center, now this carbon which was inherently electrophilic, due to presence of this dithione, it becomes nucleophilic in nature. Now it reacts with another electrophile in the medium and give us our desired product. In this way, we can just reverse the polarity of a reacting center. So by using this sulfur chemistry, we have to plan the synthesis of this cyclobutanone. Can anyone guess? For I just hint, it will start from this as a substrate, and this as a reagent. Can anyone guess how the mechanism will take place? How this reaction will take place? Okay. So it will be simple Umpolang type of reaction. If this to react fast and form this type of anion. And if you take a proton from this position, and there will be generation of negative charge here. After that, if you add this anion to this haloalkane, it will substitute one of the bromine first. Substitute one of the bromine first. After that, there is another proton is still available at this center. It can be taken up by this a base, and the anion can again react with this carbon center, generating in presence of base. This base will take this proton, so it will form this type of cyclobutanone type of ring. After that, if you just add the deprotecting reagent, that is Hg2+, what will happen? It will just deprotect the sulfur from the system and get this cyclobutanone as our product. So this question came in GATE 2021. What will be the X and Y from this reaction? So it's simple. This Umpolang type of reactivity will be here. So if you just take a proton from this position, now in presence of butyl lithium, it's a strong base. In presence of butyl lithium, this proton will be taken up, and this anion will attack to this carbon and generate any from product which is included in B and C. So A and B are already cut. After that, if you add xylene, what will happen? In presence of xylene, there will be a elimination of the sulfoxide. So in presence of xylene, if there is a positive charge, in presence of xylene there will be alpha elimination. Xylene, if there will be alpha elimination, this gets removed from the system. And in presence of Hg2+ and cadmium carbonate, there will be a deprotection of the sulfonium sulfodiethyene protection, and we get this as our desired product. Okay, so this xylene and reflux is just to remove the sulfoxonium species from the system through an alpha elimination. So the correct option is option C. Okay. Let's go to the next question. So the correct sequence of reagents to form this transformation. So let's go one by one. So suppose in the first one they have given heat. So from the product you can see there is no sulfur is remaining. So you have to remove the sulfur from the system. This is possible through using deprotecting reagent. So if we add heating in the first step, there will be no chance of any reaction because there is no such center is there. But if you add butyl lithium in the first step, there is a chance of deprotonation at this allylic position. Yes, there is a proton here. If you just keep the heating first step, there is no chance of any reaction. So let's go with the 2 first. So in case of 2, if in presence of base, this proton will be eliminated and we get this anionic species. Will form this anionic species. After that, if you add butyl bromide, in butyl bromide, it will just substitute the bromide from the species and it will enter the butyl group enter here. So we'll get this type of species. Okay, so after that, if you add this heating to it, view here, see this seems like a 1,3 dipolar addition. If this 1 1 2 3 3 sigma topic reaction, there is a possibility of 3 sigma topic reaction. So this comes here. So there is a possibility of C3 sigma topic reaction and we'll get this as our product. So 1 2 3 4 5 1 2 3 4 5 6 5 6 7 8 9. And in this position there is a sulfur. No, sorry. In this position there is a sulfur. Sulfur with a double bond. Okay. Now in presence of Hg2Cl2, what will happen? This will undergo the deprotection and there will be undergoes a deprotection and we will get this as our product. So the correct option will be option 2. Understand how we will get the idea? So suppose if you are adding heat in the first step, what will happen? This will, if we just perform the 3 sigma topic reaction here, this will go here and so there will be no chance of forward reaction. We have to enter this 4 carbon in our product. So before breaking this system, we have to enter that one, and that's why we go with the option 2, because there is a chance of deprotonation and butyl addition. After that we can just perform the 3 sigma topic reaction and then a deprotection. Okay, I hope it's clear. It was an interesting one. Let's go to the next question. This question came in the recent NEET examination. So from there you can get an idea the sulfur containing reagents and sulfur containing reactions are very important as a perspective of your upcoming examinations. So the next reagents in organic chemistry is phosphorus. So phosphorus is one of the important reagents because of its low toxicity and very strong bond formation. So phosphorus form phosphines rather like amines but also tetrahedral phosphine oxide. So phosphorus is belongs to the series of nitrogen. So it has a similar type of reactivity, and also due to presence of this vacant d orbital, it can also show variable oxidation state. So one of the important named reaction using this phosphorus is Mitsunobu reaction. So this method that allows us to substitute OH, which is a bad leaving group, and by this method through a SN2 pathway. So this is called a Mitsunobu reaction, and in this reaction alcohol becomes a electrophile and the nucleophile is usually relatively weak. So in this case, if you have a alcohol as your substrate and you want to remove the OH from the system, which is a bad leaving group, so transfer this into a good leaving group, we can just perform this Mitsunobu reaction, which can transfer this OH to a good leaving group and remove it easily from the system. So this is the Mitsunobu reaction, where if you add this PPS3 and DADE, this is the short diethyl diazodicarboxylate, in a short form we call it DADE. So if you add this DADE and PPS3, you can easily substitute this OH group from the system and add the desired nucleophile in the system. Okay. So let's go to the before going to the mechanism, let's learn something about this reaction. So what are the properties? The whole process takes place in one portion. So this is a concerted reaction, and 4 reagents all are added in one flask, leads to the inversion of configuration. Now as the reaction is going through SN2 pathway, so there will be inversion of configuration. These atoms end up in very stable molecules. The PO and NH bonds are strong, while the N and double bonds are weak, compensating the sacrifice of the strong carbon-oxygen bond in the starting alcohol. So there is an example. So if in this way, if the PP is added, it can react with this ethyl diazocarboxylate and then makes this OH a good leaving group, and this as a nucleophile can attack to this carbon center and remove the OH from the system. Now from this, here I have shown the stereochemistry of the substrate. You can see this, it was above the plane. As this center is taking part in the reaction directly, there is an inversion of this state of this center, and it gives us a product with a inverted methyl group. So this is the mechanism step by step. In the step 1, you can see this PPS3 will attack to this diethyl azodicarboxylate nitrogen and open up this carbon-carbon nitrogen double bond and form this type of species. After that, this N- will take a proton from the nucleophile and generate the active nucleophile. After that, if our substrate alcohol OH will attack to this phosphorus, and oxygen phosphorus bond is one of the strongest bond in organic chemistry. So wherever there is a chance of formation of oxygen phosphorus bond, it will always form this, and then this oxygen will attack to this phosphorus center and form this oxygen phosphorus bond, and it will remove from the system. After that, in this way, this oxygen due to the positive charge of this phosphorus group, there is a huge minus I effect which weakens the carbon oxygen bond. Because of that, it turns to a good leaving group. It turns into a good leaving group. After that, if you add a nucleophile, it can easily remove from the system and we get our desired SN2 product with the inverted stereochemistry. Okay. Let's go to the, so let's solve a question based on that. In GATE 2023, one question came based on this. So they have given these 4 options and asked for in which of the options, this can be a multiple choice question also, in which of this reaction we get an inversion of configuration. So from the reagents you can see this is date PPST, that means this is a Mitsunobu reaction and there is alcohol here. So there will be obviously inversion of configuration and we will get this as our product. Other part will be same, just this which will be inverted, and as a nucleophile they have used this acid, so we will get this as our product. Okay, I am not going into them because I have already explained the mechanism. If you are having any doubt regarding this, you can ask me. So this will be one of our option. Next is this one. So this is a, if you add heating, this is a pericyclic reaction, and pericyclic reaction are always a concerted type of reaction, and this reaction takes place like this way. So there is a formation of carbon-carbon double bond. So there is no such concept of, so this is not inversion of configuration. Next is, this is a Hofmann degradation reaction. From the reagents you have to understand which type of reaction is this. If you add this NaOH and Br2, that is called Hofmann degradation and form this type of species. So this is called Hofmann degradation reaction. In presence of Hofmann degradation, if there is a amide, it can be transferred to amine. The mechanism I am not explaining. This is a very long mechanism but easy. If you are interested, you can go and check. Just write Hofmann degradation, you can get the mechanism. In that case, just this amine group will be removed and formed. So there is no such concept. So this is just this amide group, this carbonyl group will be removed, and as a product we will get this amine. So there is no such concept of inversion of configuration. Next is this one. There is a epoxide reagent. This is a peroxide. So peroxide, it will undergo the Baeyer-Villiger oxidation, and there will be incorporation of oxygen at this center. So there is no such concept of inversion of configuration, because whenever this Baeyer-Villiger oxidation takes place, this is not reacting with this chiral center. This is just reacting with this ester center, because the ketone center. Because of that, the stereochemistry of this ketone will be unaltered. So the correct option is option A. Okay. So next application of phosphorus chemistry is the Wittig reaction. I think everyone knows about this. So if you want to form a carbon-carbon double bond, form a ketone, you can use this reaction. So conceptually, the Wittig reaction is like the base-promoted Peterson reaction. It is scene elimination and driven by the strength of oxygen heteroatom bond. Although in this case the heteroatom is phosphorus, the phosphoronium salt can therefore be deprotonated by moderately strong base to give this species known as ylide, carrying a positive and negative charge at the adjacent atom. Then the ylides can alternatively be represented by a double bond species that is called phosphorane. Now if you add PPST into this alkyl bromide, it will form this type of phosphonium salt, and if you add a base, this proton can be taken up from here and it will form this phosphonium ylide. So there is properties. Ylides can be isolated but are usually used in reaction immediately, and they are formed. So usually we take this species, this phosphonium salt, and add base in the medium, so that this phosphonium ylide generate in the medium directly and it can react. Because if you separately, if you make this phosphonium ylide and take part in reaction, this reaction reactivity of the product is not, reactivity of the reagent is not that good. So we usually take this phosphonium salt, and in that reaction vessel we add the base, and this ylide generates, and which react with our desired substrate. They are nucleophilic species, and that will attack the carbonyl group and aldehyde ketone, generating a 4-membered ring, that is a oxophosphetone ring. After that, the oxophosphetone are unstable and they undergo elimination, give a alkene with phosphine oxide as a byproduct. Phosphorus oxygen double bond are extremely strong double bond. As I said, whenever there is a chance of formation of oxygen double bond, it will always try to form that. So this is the driving force of the whole reaction. So if you now, based on the nature of the phosphorus ylide, the stereochemistry of the newly formed double bond usually varies. If the ylide is stabilized ylide, that is, if there is any electron withdrawing group adjacent to the negative charge, then that type of ylide usually give a E-alkene. That means the formed product will form a E product, like this way. Now, if the form ylide is not that much stable, like this one, if you have an alkyl group which has a plus I effect, in that case usually it form a Z-alkene. Okay. So let's solve some question based on this phosphonium ylide. So this is the aldehyde they have given, and into that they have given this ylide. So what will happen? This will attack to this aldehyde center. This will attack to this aldehyde center. O minus will open up. So this O minus will attack to this PPS3. After that, elimination of this, and there will be generation of a double bond here. So this, I'm just skipping the steps, you know about, because I've already discussed about the mechanism. So this aldehyde will transfer to a alkene. This aldehyde will transfer to a alkene. Okay. And the next one, this is also a similar type of reaction. There is an aldehyde. It will be reacting with this carbon center and form a generation of a alkene. So now, okay, this is a sulfonium ylide. This is a, sorry. This is a sulfonium ylide. So as I said, whenever this is sulfonium ylide, it will always form a Z alkene. So it will form a Z alkene. It will form a Z alkene. Now in this case, it has an electron withdrawing group adjacent to this negative charge. So this is a stable ylide. This is a stable ylide. So it will form a E alkene. form a E alkene. Okay, so this is also aldehyde. This is also a stabilized because of this minus I effect of this aldehyde group. This will react with this aldehyde center and will give us this type of E alkene. Okay, let's go to the next question. Boron containing reagents in organic chemistry. So boron is one of the important reagents. So boron and the organic borons easily add to a carbon-carbon double bonds. The boron atom subsequently can be removed from these adducts by using the several reagents by a reaction which use the ability of the boron atom and to accept the electron pair. These factors are responsible for the synthetic application of boron. So if you add this boron into the alkene double bond, what will happen? It will be added to the across this double bond, where this boron will go to the less substituted double bond, less substituted carbon, and the hydrogen will be added to the more substituted carbon and undergoes a chain addition of this boron and hydrogen. So if you see the application, if you take this boron and react with this type of carbon-carbon double bond. Now if you add this hydrogen peroxide and OH minus, this boron will be replaced with OH and it is generation of carbon-oxygen bond. So by this chemistry you can also form a carbon-oxygen bond just by substituting the boron from the system. So basically if you react this 9 boron reagent with a hydroboron reagent with a alkyne, what will happen? So let's go step by step. So as we know that boron will add to the less substituted less substituted carbon. So here the less substituted side is this one. So boron will add here. So boron will add here and the hydrogen will be added at this more substituted carbon center. After that, if you add H2 NaOH, this carbon boron bond will be replaced by a oxygen and it form a OH. After that, it will undergo the tautomerization and form a aldehyde as our product. Okay, I hope it's clear. Let's go to the next question. So there's an application of this boron chemistry. We can also use, we can also form a carbon hydrogen bond in place of carbon boron bond. If you add acetic acid, this carbon boron bond can be replaced by a carbon hydrogen bond. These are the short things you have to remember in case of you can use this in as a synthesis of some large molecule. By using this acetic acid, you can easily replace this carbon boron bond with a carbon hydrogen bond. So this, if you add this hexyl boron into this alkyne, this carbon boron will be added to this less substituted carbon center and hydrogen more substituted. After that, if you add another molecule, another alkyne, it will undergo same type of reaction, and if you add the nucleophile, it will be added to the boron center, and then by addition of acetic acid, it will be added to the boron center, and it undergoes this type of substitution reaction. This goes here and this chlorine removed from the system, and if we add acetic acid after that, this carbon boron bond will be replaced by a carbon hydrogen bond, giving us this as our desired product. So in this way, by addition of a nucleophile, you can this boron can also take place in a substitution type of reaction, where this, if it is a negatively charged, this undergoes this type of 1-2 elimination and give us our desired product. So let's solve some questions based on this boron chemistry. So what will be the major product P and Q in the reaction sequence? So let's go step by step. So if you add 9 PBN, boron will be added to this less substituted side and carbon will be added to the more hydrogen will be added to the more substituted one. So suppose they have taken this as a below the plane, so obviously the 9 BBN will approach from the above the plane. So boron will, this due to presence of this carbon-carbon bond, tertiary carbon, this center is bit bulky, so boron will be added to this plane, whereas the hydrogen will be added to here. After that, if we add NH2 to NaOH, carbon boron bond will be substituted by a carbon oxygen bond. And form this as our product P. So this will be our product P. So option, these two are already cut, so correct option will be between C or D. After that, if you add acetyl chloride and ET3N, this OH will be methylated and transferred to a good leaving group. This OH will be methylated and it will become a good leaving group. After that, if you add NaOH, this ester will be hydrolyzed and form this acid. So this is after the two step. If you add 1, this methyl chloride, this OH will be methylated, then you have add 2, this ester will be hydrolyzed and will form this. Then this can attack to this carbon center, adjacent carbon center, and this goes here and OM will be removed from the system. So as this is below the plane and this is above the plane, it should appear from the opposite plane of this OMS, and this is already below the plane, so it will form this as our product. this type of lactone as our product. After that, if you add this reducing reagent, this double bond, this Wilkinson reagent, this is called Wilkinson reagent, Wilkinson catalyst. This is called Wilkinson catalyst. Wilkinson catalyst. So this Wilkinson catalyst will reduce the double bond and give this as our desired product. So the correct option is option D. Correct option is option D. Okay. Let's go to the next question. So this is also belongs to this boron chemistry. I am giving this as a homework. Just try it. We'll solve it in the next class. So if you add this B2H6, what will happen? B2H6 is specific to the acid hydrolysis. So it will reduce this CO2H group. Reduce this CO2H group. After that it will react with this ester moiety, internal ester center, and remove the OMe from the system, and as a product we will get B as our product. Understood? So this type of B2H6, BH3 all are specific to acid hydrolysis. All are specific to acid hydrolysis. If there is a two react acid and ester, it will specifically react with the acid center. So in presence of NaOH, base, this can undergoes a elimination reaction. This can undergoes a elimination reaction. So for whenever there is a SN2 reaction, there should be an anti-elimination. So this H and Br should be at the opposite plane. So as this is a single bond, it can there can be a bond rotation is possible here. So if you just rotate this bond, this H comes here. So this can easily undergo elimination, anti-elimination, because H and Br are not in the same plane anymore. There is a OH here. And there is a methyl here. So in presence of so what will happen in this case? So in this case, this is if in presence of NaOH it can undergoes it can undergo the anti-elimination, but if you can see the adjacent H and bromine are not anti to each other, they are in the same place, they are in the same plane. So what can be done? But there is a OH which is in the opposite plane of this. So the OH group is already at the antiposition of this bromine, so it can easily get removed from the system. So if this comes here and this bond goes here and this bromine removed from the system, we get this as our product. There will be a generation of aldehyde. There will be a generation of aldehyde where the methyl will be intact with this stereochemistry, and there will be also a generation of a double bond. What will be the stereochemistry of double bond? This is a E double bond. After that, in the next step, if you add NaBH4, this aldehyde will be reduced by this NaBH4 and form this alcohol. So we will get, so as this is E alkene, so these two are already cut from our options. These two are cut from our option. So as this methyl group is below the plane, in this one this is below the plane, so the correct option is option 4. Okay, correct option is option 4. Let's go to the next question. So what will be the major product formed in the following reaction? Whenever there is a silicon and if you add a bromine, it usually normally in case of methyl, when you are doing some Friedel-Crafts reaction or bromination reaction, usually it undergoes a orthopara orientation or a meta orienting electrophilic substitution. But instead of methyl, if you add a SiMe3 group, a TMS group, it usually shows a ipso substitution. It usually shows a ipso substitution. What does it mean? This will attack here and form this type of sigma complex. So I just draw the arrow. So it will be attacking through the same center of the where the silicon is attached. In the next step, as silicon also act as a good leaving group, also acts as a good leaving group. So instead of hydrogen elimination, it can be eliminated, and this will be as our, we'll get this as our product. Okay, so there is at the Br minus is as there. This Br minus will attack to this silicon, and it can be removed from the system as because of silicon as a good sub. So whenever there is a SiMe3 in your aromatic group, it usually undergoes a ipso substitution. It will undergoes a ipso substitution. Let's go to the next question. So among these four options, which will show a chemoselective reaction? So this LiBH4 is added. We know that LiBH4 is selective to ester. LiBH4 is selective to ester. B2H6 or BH3 is selective to acid, but LiBH4 is selective to ester. So in this case, this part will react, not this one. If you add this Ag2, this is this Ag2 silver carbonate and silide. This is called I can't remember the name of the reaction. So this type of reactions are usually specific to allylic alcohol. So this is a allylic alcohol. So this alcohol will react faster than that of this. So this is also a chemoselective reaction. Chemoselective reaction, if you have a two reacting center and your reagent is reacting with one of the reacting centers specifically, that is called a chemoselective reaction. Stereoselective means if you have two different stereochemistry of your substrate and one single stereochemistry is reacting selectively, that is called stereoselective. And another one is regioselective. If you have two reacting center and we have its same functional group with the two reacting center and it is reacting specifically with the one side, that is called regioselective. And chemoselective is two functional group and it is reacting with one of the functional group, that is called chemoselective. Functional group selectivity is called chemoselective. So whenever there is a allylic alcohol and normal alcohol, it is specific to allylic alcohol. So this is also chemoselective. There is only one double bond is there, so there is no such selectivity seen in case of H2 platinum hydrogenation. It will always give a scene addition. So this is not a chemoselective reaction. This is actually a stereoselective reaction. In this case, this attacks, this iodination will take place here and this will attack. So this is also a regioselective reaction. This is not a chemoselective. So correct option is option A and B. Because if it, in this case, the reaction goes through like this way, there will be iodination here. Then this adjacent acid group will attack to this carbon due to formation of 5-member ring. It will open up. So this is not a chemoselective reaction. In this case, it will specifically react with the allylic alcohol and undergoes oxidation to form this ketone, and this normal alcohol will be intact. Whereas in this case, this ester group will be reduced specifically to give us alcohol. So this is our product. So the correct option will be option A and B. So what will be the major product formed in the following reaction sequence? If we add sodium liquid ammonia into this orthoxylene, what will happen? It will undergoes a Barch reduction, forming this Barch reduced product. After that, in the next step, if we add this Wilkinson catalyst, the hydrogenation will take place, and it will specifically hydrogenation of this electron rich double bond, hydrogenation of this electron rich double bond. Now if you add BH3NOH, BH3 and so it will be OH will be added into this double bond. So there will be a so the correct option will be option 1. Sorry. So this specifically this double bond will be reduced because it's less bulky. This is less bulky. So after that, if we add now there is a double bond here. Now if we are adding BH3, so it will approach from the same plane. So if it is going above the plane, BH3 will come to the below the plane. BH2 and hydrogen will both will come from the same plane. And when you add H2 to NaOH, this will be this carbon boron bond will be transferred to a substituted with the carbon oxygen bond, and we will get 3 as our correct option. We will get 3 as our correct option. You have to see the stereochemistry of the product also. Between 2 and 3, here the stereochemistry is trans, but it is not possible because the BH3 addition will be always cis, and this Wilkinson reduction will be always in a cis manner. So then both the methyl group should be cis, and both this OH and H should be also cis in the manner. Let's solve the next one. So what will be the major product formed in the following reaction? So what will be the correct option for this reaction? Let's go step by step. In the first one, if you add MCPB and NaBH3CN, if you add MCPB, what will happen? It will form a epoxide, and if you add NaBH3CN, it will be BF3 will coordinate with this oxygen center, and it will open up to form the more stable carbocation, and hydrogen, then H minus will approach from that plane. So this is more stable carbocation because this is tertiary, 3 degree. Then H minus will approach here. Suppose this is forming from the above the plane. Okay. Now, so this OH will be above the plane. But in this case, when this becomes a carbocation, we get a 50% of this product, 50% of this one, 50% of this one, and 50% of the anti one. Because there is a formation of carbocation, so H minus can approach from any of this plane. Okay, so 50% of this one, 50% of this one. Let's go to the next one. What they have said: if you add osmium tetroxide and NMO, what will it will undergoes a dihydroxylation. So if it is methyl group is already there, if it is dihydroxylation, then the OH, both the OH will approach from the below the plane. Now if we add TACL, this will be this OH will be tosylated, and by addition of this LiLH4, this OH become tosylated, and addition of this LiLH4, it becomes substituted, and we get this as our product. This is not our desired one also. So then let's go to the next option. If we add MCPPA, and if we add LiLH4, it will attack to this less hindered side, forming this as our product, which is not right. Next is this one. Here they are using a benzoic acid, so there is no such benzoic acid is there, so this is also not possible. So correct option is option A. Let's go to the next question. So the correct statement for the following reaction. So this is a thioester, so it is a Chugev reaction, xanthate ester. So this is called a Chugev reaction. So in presence of heat, it will undergoes a syn elimination. So there is no such syn hydrogen. This hydrogen is anti to this leaving group. So there will be a ring inversion, bond inversion. Because of that, this leaving group becomes in the same plane of the hydrogen, and it undergoes a syn elimination. It undergoes a chain elimination and form this as our product. So it will be a chain elimination and this as our product, because the ring has been, so methyl group is at the same plane of this other one. Both the methyl group is in the same side. Both the methyl group is in the same side. So this will be our correct option. What will be the major product formed in the reaction sequence? So MnO2 is selective to allyl alcohol. So this will be oxidized. This alcohol will be oxidized. This center will be oxidized, specifically become aldehyde. After that, if you add a protecting reagent, then it will be protected. It will be protected. After that, if you add PCC, this OH will be oxidized, the remaining OH will be oxidized and will give this as our desired product. Okay. So this is the last one. Which of these reactions will yield 3-phenyl cyclopentanone as the major product? Which of these will yield 3-phenyl cyclopentanone? So let's draw the structure of the 3-phenyl cyclopentanone first. This is cyclopentanone and 3-phenyl cyclopentanone. So there will be a phenyl group. So which of these will give 3-phenyl cyclopentanone as a major product? If we add this one, it will attack to this side and form. So this can give also 3-phenyl cyclopentanone as a major product. So this can be one of their option. Next is this one. If you add phenyl iodide and catalytic, so there will be a chance of, so it will, if you add a phenyl iodide and PDOAC hold 2, there will be chance of heat type of coupling. But whenever there is electron donating group like OH, it usually approach from the alpha position of the, so this is not possible. This is not possible. Next is this. If you add phenyl lithium, it selectively approaches to the carbonyl center. This is the difference between if you add phenyl copper lithium, it will approach to the beta position. If you add this, I will discuss when we will discuss about the Grignard reactions. Sorry, this will be oxygen lithium. Okay, so this is not possible also. Next is this one. If you add LDA, there will be a generation of negative charge here, alpha position. Then if you phenyl selenium bromide, it will enter, phenyl selenium bromide will enter here. In the next step, if you add this H2O2 NaOH, H2O2, this selenium will be oxidized. Selenium will be oxidized and undergo a 1,2 elimination. Then it will undergo 1,3 dipolar. So this H, in presence of this H, will be trapped and it undergoes a elimination type of reaction, giving alpha beta unsaturated double bond. So the correct option is option A. The correct option is option A. This is not our desired one also. So the correct option is option A. So this much for today's class. I hope it will help you to solve your upcoming assignments. Thank you everyone. Have a nice day.